Okay, well, I guess we should just go ahead and get started here. So, the setup that I've got right now is that I've got a few of folks from class on Zoom. So, hello to those of you who are on Zoom. And then I'm also streaming this. It'll be slightly delayed, but mostly in real time on Twitch. So right now I'm seeing nobody in the room on Twitch, and that's totally fine for now. That'll also be nice for recording this so that I can post it later. So hello to those of you who are watching on Twitch. My webcam is up on that, but I don't have the webcam broadcasting in Zoom because I am sharing the screen in Zoom. So a note to those of you who are in class, your audio is not going through the broadcast. So you can talk and that will not be, anything you say will not be broadcast. The only thing that is being broadcast is my voice. So those of you listening to this recording on Twitch, if there are gaps where I'm just kind of nodding my head as if something was happening, that's probably because one of the students in the Zoom is chatting. And I'll do my best to repeat questions. So those of you who are in the Zoom call, please feel free to interrupt at any time. I see you all have your mics muted right now, which is great. Good chat etiquette. But feel free to interrupt at any time. I mean, just unmute your mic and start talking while I'm doing something, and I'm happy to stop. All right. So I guess we'll just kind of start working on the lab. So I've got my console up, and that should be shared on both Zoom and on the Twitch stream. And so I'm just going to work through the lab. So it'd probably be most useful for everyone to kind of have the lab up while we're doing this. In particular, it's useful to have the graph. So for those of you who are in the Twitch, um, I'm just going to show you the graph really quick so that you know what I'm talking about. Hopefully everyone in Zoom knows what I'm talking about. So those of you watching on Twitch, you can see this graph here. It's just basically the language ancestry graph. And the way the arrows work is that they point to a language's ancestor. So for instance, here you can see that Scheme's ancestor is Lisp. And so it'd be useful to have that open while we work through this. So I've got it up on a window off to the side. Okay, so I've logged into the student server. This is where I recommend people work on things. You can do some of this in the interactive interpreter online, but as you work towards doing the programming assignments, you're going to want to have a place where you can run things from the command line. So probably better to just start from this. So I'm going to use Oh, I was already running Tmux, right? So I'm going to use Tmux in order to have both Prolog and my editor open at the same time. So I'm going to have Lab 5 open here on the side. And I'm just going to use Vim for my own sanity. But those of you who are following along with this later, or if anybody in the Zoom wants to follow along right now, you can use whatever editor you want. Okay, so we start with just pasting in a bunch of facts. And so in Prolog, a fact is just an association between atoms. So these lowercase things are called atoms, and then the relationships between those atoms are just referred to as facts sometimes, or relationships or predicates. There are a lot of different terms that we use for them. So this basically just says that the direct ancestor of Scheme is Lisp. So that encodes that arrow that I highlighted um, in the graph. So we're going to go ahead and save this and go over here. And so every time we modify the file, we'll need to reload it. You can do listing to see a list of everything that's there. That's probably not terribly useful. But what you can do is you can list out particular pairs of things that are in the direct ancestor relationship by putting in what are called variables instead of atoms. So the atoms begin with lowercase letters and variables begin with uppercase letters. So here we can just say, what are all the pairs of x and y such that x has direct ancestor y? So this is going to start giving us those relationships. So this is the first one. scheme has direct ancestor Lisp, and then we can either say, all right, that's enough, I don't need any more, in which case you would press enter, or you can say, can you give me anything else? And in order to do that, you just press semicolon. So this is now going to give us all of those relationships in the order in which we gave them, it seems. So probably what's a little more useful is to ask more specific questions. So for instance, we can say, well, what are all of the languages that are considered to be the direct ancestor of Java? So you'll notice here we put in an atom here on this side of the predicate, and then we have a variable on this side of the predicate. So this will give us all of the x's for which it is true that Java has direct ancestor x. So here it's Smalltalk and C++. Okay. Oh, really? Interesting. Okay, so I just got some feedback from the Zoom that the screen is frozen. Let me attempt to stop the share and restart. All right, how's it look now? And if I do this again, can you see that change? Okay. Okay, cool. Thank you. Thank you for that. I am assuming it's still working on Twitch. Still nobody watching live there, so that's fine. Okay, cool. So that's sort of the relationship between atoms and predicates, which we'll sometimes refer to as well. These are particular encodings that we call facts. And so I think at this point the lab has us beginning to define rules, if I remember correctly. Yes, so the next thing we do is we define ancestor. So I guess I'll pause at this point and see if there are any questions from folks in the Zoom. Okay, so hearing no questions. All right, so the next thing we want to encode is an ancestor. So you'll notice that we have direct ancestor here. So this is just gets us all the little arrows in our graph. And so what we want to do is we want to encode sort of the transitive ancestry relationship. So not only direct ancestor, but ancestor to any degree. So for instance, we want to be able to say that, Haskell has ancestor Lisp, even though Haskell does not have direct ancestor Lisp. So we need to make this definition. And so one way of defining this is to just say, well, there are two cases, right? So there is the case where, so A and C, and I'm using A and C here because we'll need a B in the next one. So one case for A having ancestor C is that A just has direct ancestor C. So that's sort of the first case. So the colon dash is, you can read this as sort of saying if, right? So A has ancestor C if A has direct ancestor C. So that's one case. But at this point, ancestor really isn't anything other than a synonym for direct ancestor. So what we need at this point is to make it transitive. And so what we can say is that, well, another case for A having ancestor C is if, A has some direct ancestor B, and we read the comma like an and. So if A has some direct ancestor B, and recursively B has ancestor C, then we say that A has ancestor C. And you'll notice that that is a recursive definition there. So we used the definition for ancestor in the definition of ancestor. which is why we need a base case, which is this line right here. All right, so now that we have that, we'll need to reload again. And so now we can make queries about ancestors. So now we can say, well, what are all of the ancestors of Haskell, for instance? So we get scheme and we get Lisp as we had hoped to get. And just to show you, sure, okay, something just changed on my screen. So direct to ancestor Haskell. So we can see that only scheme shows up there. Is the display still updating for those of you who are in the Zoom? Something weird happened on my screen, and I don't know if it's still updating. Okay, awesome, thank you. And again, for those of you who joined late, I'm working through the lab. Those of you who are in Zoom, feel free to unmic and ask a question at any point or interject anything. I am also streaming this to Twitch, which is doing a recording for me so that I can post it to YouTube later. But your voices will not be either broadcast or recorded. They are going straight to my headset, and so the only things that are being recorded are my voice. Okay. I just realized that my music was still playing. I had the volume down, so nobody was hearing it, but that was probably hurting my bit rate. Okay. So questions about how we defined ancestor. Once you're comfortable with this, I think a lot of the rest of this really kind of follows relatively straightforward. So if there's confusion at this point, we should make sure that everybody is on board with what's going on here. Yeah, so maybe maybe we can put in some comments here. So so A has ancestor C. If A, what in the world is up with the? Oh, that's right, that's right. Yeah. So for Vim, I need to make the first line a comment. So there's this weird thing in Vim where so the weird thing is that both Prolog and Perl have the extension PL, and so in order for Vim to infer that you're working with a Prolog file, you have to start the file with a comment because the comments are different. Okay, so A has ancestor C if A has direct ancestor C. And so that's one case, right? And then the other case is or if A has direct ancestor B and B has ancestor C. So in essence, this is transitivity. So the picture here would be A arrow C in our diagram. And then down here, the picture would be A arrow B, and then some sort of path from B to C, where this relationship right here does not necessarily need to be a direct ancestor relationship, but rather, following some chain of links by sort of recursively expanding. So maybe it would be, so for instance, so if I were to query and say, well, is direct ancestor, so does Haskell have direct ancestor scheme? That's true, right? It does not have direct ancestor Lisp. However, Haskell does have ancestor Lisp, and it does so through scheme. So what's happening under the hood here is that, Haskell becomes A here, Lisp becomes C, and it tries to find some B such that this definition that we've written here is true. Does that help at all? And notice that it paused there, right? Um, because it showed that Haskell has ancestor Lisp, and it did so through Scheme, but it's also giving you the opportunity to say, hey, I know I found a link through this one intermediary. I might be able to find another link through another intermediary. Do you want me to continue? So that's why it pauses there. But of course, there is no other way to do it, so it just finishes, giving you the slight confusing result here where it was true at first and then it was false. But the second false was because we had already gotten it through Scheme, and then we told Prolog we wanted it to find it another way, and it couldn't find it another way. So that's why it got the false there. Does that make sense? Okay. Okay. All right. So what's next? So I think next we define cousins. I have a million windows open right now. Yeah, so we want to define cousins, which is true x, and if we want, let me go ahead and just start typing this. So we want cousins x, y, which is true. So this is going to be true if, so x has cousin y if they have an ancestor in common. So the way we need to encode that in Prolog is by making statements and using the variables in those statements to make some sort of assertion. In this case, we want to say that x has some ancestor and y has some ancestor, and that ancestor is the same thing. So that's what we want to encode here. Question from the Zoom chat. So for those of you arriving late, feel free to unmute yourself in the Zoom and ask questions verbally as well. I am broadcasting this, but your chat is not going to be broadcast. Okay, so the question in the chat is the subject of a rule always going to be the first parameter? So I'm not quite sure what you mean by subject. So these predicates are always defined by us. We get to define what it means, for instance, to say, so here, right, we have this predicate that is, direct ancestor, say x and y. And it's up to us to define what this means. So we could have defined this as meaning x is the direct ancestor of y, right? But we defined it the other way around. We said that this means that x has direct ancestor y. So I think that I think that answers your question. So it really is up to the person who is defining these things to say what it means. And so in this case, it doesn't really actually matter because the relationship should be symmetric here, right? So we should be able, cousins x and y should give you the same value as cousins y x, right? So that is hopefully something that is true if we have defined this correctly. Okay, so again, we need to express that they have an ancestor in common. So we're going to make some statement about the ancestor of x. I'm just going to leave that open for now. We're going to make some statement about the ancestor of y. And then I think there's also the stipulation that, so you don't want a language to be a cousin of itself. So that's one of the things that it says in the lab. And so we say, we mentioned in the lab that one way of doing this is to use the predicate x not equal y. And I think you can write it like this. So that maybe that's a little bit clearer than what's in the lab. So basically, we're not going to let anything be a cousin of itself. Okay, so the way we express that they have the same ancestor is just by using the same variable. So we can use any variable name that we haven't already used. So maybe we'll use z here because we haven't used that already. So, X has ancestor Z, Y has ancestor Z, and because Z needs to be the same thing in both of these clauses, then this will essentially say that they have to have an ancestor in common. So let's reload. And first of all, let's just do some factual checks. So we would expect, for instance, Simula and C to be cousins, right? Because they have algyl and Fortran. So that is true. And you'll notice that it paused again because it was able to prove that they are cousins via algyl, but there might be another way for it to prove it, and so it's asking us. And if we ask it to do so, then it does in fact find another way to prove it, and that's through Fortran. And so then at this point, it should probably fail. Yeah, so those are the only two ancestors that those two things share. If we run a pair that we would not expect to be cousins, so for instance, Scheme and Java, these two languages have nothing and no ancestors in common according to our graph. So we get back false. And of course, now we can do some more interesting queries like, well, what are all of the cousins of Haskell? Maybe this is not an interesting one, but so Scheme and Haskell have the same ancestor. Scheme and Common List have the same ancestor, and that's it. So maybe one that is more interesting is something like C++. So C++ is going to have a lot more cousins. And you'll notice that we're getting some of these more than once, and that's because they have more than one ancestor in common. So that's a lot of ancestors. There we go. And this should be symmetric, so I'm going to go back to this one because there's fewer results. So we should get the same set of answers by saying which things have cousin Haskell. Yeah, and we get the same things. We wouldn't necessarily expect to get them in the same order, I don't think, but we would expect to get the same set of answers. Okay, questions about that? Does that making sense to everyone? Now nobody is responding. Are you all still there? Still there? Okay, thank you. It's this is so aggravating. I can't see any of you. I can't see you nodding, or I can't see when you're squinting and your brow is furrowed because you're unsure about something. Okay, so what are the next things? So next we have common ancestor, and this should be a piece of cake, right? Now that we have cousins, right? Because common ancestor is really just these first two bits, right? So common ancestor. So X and Y have common ancestor if, or sorry, the definition is a little bit different. So X and Y have common ancestor Z if this is the case. And that is the exact same definition, except now we have the actual ancestor, right? So now we can say, common ancestor Haskell scheme X, and now it says, oh, whoop, I forgot to reload. So now it says, oh, they have ancestor Lisp. Incidentally, if we had done these in reverse order, it would have made far more sense to define cousins using common ancestor. So we could have said that X and Y are cousins if, they have some sort of common ancestor and X is not equal to Y. Now, I'm going to get a warning on this, I believe, and this is actually a good place to introduce this. Yeah, so I got a warning here. And I believe there's already been a Piazza post about this as well. So it's warning me about something called a singleton variable here. Now it should still work. So I should still be able to say, cousins Haskell X, and I'll still get scheme and common Lisp. But what's happening here is that it's warning me about my use of Z here. It's noticing that Z is not really used anywhere else. That's why it says singleton. And that's not necessarily a problem. It just means that we've given something a name without ever referring to it again, which in Prolog is kind of an indicator. This would be like if you had declared a variable in C and you never used that variable. And so the C compiler would probably, if it were configured properly, it should give you a warning about that and say, X defined but never used, right? Which is usually an indicator of a bug or of some feature that you took or some solution approach that you took out and forgot to remove the definition. So I would urge you to treat these warnings from Prolog like the warnings you would get from your C compiler. Generally, they are indicators that there is some kind of problem with your code. Even if that problem is just, well, I don't really need to give Z a name, so I can use this thing that I think we saw in Haskell as well, where I can replace the name with an underscore. And so now I'm not giving it a name. I'm just saying that there needs to be something for which that statement is true. And so now when I load it, I don't get that error anymore, and cousins still works. So that hopefully is an explanation of that Piazza question if folks were still kind of confused by that. Okay. Questions at this point? Okay, so this is, alternative definition for cousins using common ancestor. All right, so I think we are approaching the end of the lab, although we haven't done any tests yet. We've just been kind of running tests arbitrarily from the interactive interpreter. So let's go ahead and finish up the implementation, and then we'll talk about how testing works, and then we will take a look at the programming assignment for this week. So the last thing that we want is something called progenitor. And so let me find the definition here so I don't misspeak. So we're going to have a one-place predicate called progenitor that is true of a language if it has no ancestors, but at least one descendant. So a progenitor must have descendant. So if X is a progenitor, what that means is that there must be some value such that X has ancestor X, right? So that's the easy part to understand there. Again, if we were to put some variable name here, we would get that warning about singleton variables. So we can avoid that by not giving the variable a name. So this is the must have a descendant part, and then. But at this point, anything that has a descendant is a progenitor at this point. So for instance, Pascal is a progenitor at this point. And we don't want Pascal to count as a progenitor because it does actually have an ancestor. So the only things that won't be true here are things that don't have a descendant like Ada. Okay, so let's code up the rest of this. So what we want to be able to say is that this is true, and it is also not true. And so in Prolog, we have this little operator that reverses the value of anything that you put inside of it. So we're going to say that it is not true that X has any ancestor. So that's the second part of this definition. So there must be something that has X as an ancestor, and it must not be true for anything that X has ancestor anything, basically. So you can think of the underscore as something of a wild card, sort of. All right, so now we should be able to say progenitor Pascal. That is now false. It is still false. And then when we try something that is a true progenitor like Fortran, that should be true. Yes. And in fact, it is true in many different ways because it has many descendants. And so it's probably not terribly useful here to have that happening. So one other thing that we can do here is we can use the cut operator to say, well, once we've proven this one way, we don't need to keep trying to prove it in other ways. So now we can just say progenitor Fortran and it just says true. All right, questions? Is that all making sense? And I think we only have 2 progenitors in this graph, but we could verify that, right? By running this with a variable instead. Right. We would need to remove the cut if we wanted more than one. The cut just basically says stop after finding one thing. And we'll have to reload. Right, so now we see Lisp and Fortran. And again, for now, we're getting duplicates. It would be fairly complicated to remove the duplicates at this point. You could do it with lists, but we're not going to talk about lists until the second prologue module. So. Okay, so the last thing that was in the lab is just a little bit about testing here. So we've just been testing arbitrarily, but it's nice to have some formal test routines. So I'm just going to copy in this test case that was provided. So this says, and I actually like writing them like this. So this is a predicate, and you'll notice that it has no parameters here. So for this week, we don't need to worry about duplicates. Correct. As you'll see here in a second, we're only sort of testing true and false assertions. We are not testing anything that requires building lists of things. Now we will do that not next week, but the week after that when we do our second Fortran module. And so we will need to worry about duplicates at that point. Okay, so this is the test case for, we don't need that comment. Test for cousins. And so you'll notice that this has no parameters, right? There's nothing in parentheses here. So this is just an assertion. So test cousins is true if Java and C++ are cousins and Java and Lisp are not cousins. So if we look at our diagram, we can verify that that's the case. Theoretically, we could put a line in here for every pair of atoms in our graph, and that would be an exhaustive test case. I'm not going to do that right now because that would take a long time, but we've put enough in here, hopefully, to verify that this is working. So test cousins, and that is true, and again, it's going to tell us all the different ways in which it's true, and so we probably want to have a cut, but we actually, we probably don't want it here. So just to show you, all right, so that kind of short circuits after a success. We probably don't want the cut here. We want the cut at the top level testing routine. So I'm going to go ahead and leave this here for now. Although also we should make sure that the test returns false if we have a broken implementation of cousins, right? So one thing we might want to test here also is that Java is not a cousin of itself, right? So this is something that should be true right now. Yep. And then if we come up here and we break our implementation of cousins by omitting that clause, this is now false because we are now able to prove that Java is a cousin of itself, which violates this clause of the test routine. All right, so let's fix our implementation here and verify that we have fixed it. Okay, cool. Yeah, and so then the lab just says, well, you should write test cases for the others, and then chain them together. So test common ancestor. So let's see here. I'm just going to look over at what we've got. So Java and CPP have some ancestor. We should probably have a negative. So testing with negatives is actually really important because it's fairly easy to write a predicate that works for all the pairs for which it should be true, but it's often harder to write a rule that works for all the cases where it should be false. So we should also say, scheme and C++ do not have a common ancestor. So it's just as important to test with the negative test cases here. And so the point here is that we can chain these together by saying, well, overall the tests should pass if test cousins passes and if test common ancestor passes. And here's where it's nice to have the cut because you really only want to know true or false for these. You don't want to have to get back true multiple times. So test is true. Again, if we were to break our definition here. I think I can break it by doing this. Oh well, we know that we can break it by getting rid of this clause. We've done that already. There we go. Okay, so that's the basis of testing in Prolog. And then for the project, I'm also providing a convenience bash script that runs these individually because you'll notice that when it failed, it did not tell us which test failed, which is a little annoying. And so the testing script will run each test individually and tell you which ones failed. Don't we need to write a test for progenitor? Oh yeah. We would need to do that too. So we would need to do test progenitor. So for instance, we would want to make sure that both Lisp and Fortran are progenitors. And again, it's just as important to test that something that is not a progenitor like Java is not considered to be a progenitor by this code either. Okay, so that's our full test suite, and hopefully that is passing. All right, cool. All right, so questions. That is, I believe, the solution to the lab. I think I'm going to stop broadcasting these things on Twitch. There's nobody there. Because I can record them in Zoom as well. Twitch seems to be working fairly well for the interactive lectures in 470, but doesn't seem to be a popular option for the office hours. Okay, so not seeing any or hearing any questions, so let's go ahead and talk a little bit about the project. So let's go ahead and grab the project. That would probably be a good first start. So I'm going to copy the link. So I'm going to download the zip, unzip, zip, and go into it. Okay, so over here, I'm going to open up facts. Oops, it would help if I were in the correct directory. So I'm going to open the facts file, the testing file, and the solution file. So actually all the prologue files here. Okay, so the lab is some family tree stuff. So this is actually very, very close to what you did in the lab, except working with people names instead of language names. But there are going to be a lot of similarities, as you might imagine. And so a lot of the things that we just did in the lab will be almost directly copied over into the project, or just adapted a little bit. So this file contains facts about a family tree. The primary relationships that we have to work with at the beginning are spouse and parents. So this indicates that Mary and Edward are a spouse, and note that this is symmetric, so it doesn't matter what order we ask the question, we will get yes either way. And then this parents relationship. So this basically says that Kelly has parents Bill and Mary. So if we have parents X, Y, Z, X has parents X and Y. And you'll notice that this reads the same way that the predicates from the lab read. And again, this is just us saying that this is how we're going to interpret this. We could have just as easily said that, oh, well, this means that Kelly and Bill are the parents of Mary, right? So it was the only reason that we interpret it the way we do is because we said that is how that's going to be interpreted, and so that's why the project spec is very explicit about how to read each of the propositions, because being able to read them properly is key to being able to understand and implement them. All right, so those are the facts, and I would encourage you to draw out this family tree to get a graph like the one that we had for the languages. I've thought about distributing this with the project, but I've determined that I think it really helps for everyone to kind of think through these relationships and draw it yourself. So if you would like to compare notes with other folks that you know in the class, I'm happy to allow that, but I am going to specifically refrain from posting my image of this family tree, because I want you all to go and try to draw that yourself. I'm just curious, has anybody in Zoom done that already? I will take the silence as a no. Ah, gotcha. You didn't draw one in the 10 seconds that you've had? Yeah, it's there are some weirdnesses, because there are one thing that trips people up is that there are some parents who are no longer spouses. Where is an example of that? Oh, well, the very first one is an example of that, right? Because Kelly has parents Bill and Mary, but you'll notice that up here Mary is the spouse of Edward, right? And Bill does not appear anywhere in the spouse list. So the family tree is a little bit sprawling. But in any case, so those are the facts. These are the test cases that we have provided. You should probably add in a few more of these. Yes, I do suggest sketching out all the relationships just for clarification. Yes. So these are some test cases. Again, I would encourage you to fill in some more of these, especially if you can identify some edge cases that we did not provide to you. I would recommend adding those in. But these are the tests that we're giving you. Incidentally, while we've got the tests up, let's go ahead and also look at the testing script. So not sure that I can actually get the whole thing. Yeah, so that's a really long line of code. But that's not actually what we're using this year. So you'll notice up at the top that you can toggle between using GNU Prolog and SWI Prolog. We were using GNU Prolog up until last year, and it was giving us a lot of problems. So we decided to switch to SWI Prolog for this year. That's what we're doing. So it keeps track of the number of tests that fail and the number of tests that succeed and the total number of tests. So basically, we list the tests down here. So you'll notice that these names here are the same as the names of the predicates. So for instance, here's test in law, and then here is the same test name here. So that's what ties these two files together. But then run query is just a bash function that takes that name and runs SWI Prolog and tells it that so running it with these options here means that it doesn't run interactively. It just tries to prove the predicate that you give it. And this is just bash syntax for the first parameter to run query. So for instance, this line right here is going to run prolog, and it is going to attempt to deduce your, it's going to attempt to prove test parent. The only other shenanigans here are that we're actually creating a temporary file here that has all the facts and all of your implementation and all the test code in it. That's just to make things a little bit easier, and we're passing that file to SWI Prolog. Okay, so the long and short of all of that is that you can run test.sh and it will tell you exactly which tests you are passing, which of course at this point is none of them. Oops. Okay, so let's go over to the solution. So here are the functions or the predicates that we're asking you to implement here. So we're asking you to define parent, step-parent, sibling, aunt, uncle, grandparent, ancestor, relative, and in-law. So my plan was to simply oh, I just got an email from somebody in Twitch chat who says that they have been asking questions and I haven't been seeing them. Really? That is bizarre. So the only chat that I have been seeing so far has been coming from Zoom. Oh wait, now I see people chatting. I just reloaded my my stream manager. Oh man. Okay, so that's really annoying if it was not showing folks before. Are you able to, I'm getting a question in Zoom right now. What do you mean by run? Well, so you should treat the test.sh as your main, essentially. If you just want to test the individual predicates, I'll show you how to do that in a second. Oh yeah, okay, all right. Well, that's really annoying because until I refreshed, it told me that nobody was in Twitch chat and nobody was chatting. Okay, so yeah, okay, so now that I've refreshed, I see Ripley and Commander Root and Dr. Griff, J Griff, hey, Lurks and Paul Jobby. Okay, right, yeah, so we definitely have folks on Twitch, and I have. So, yes, so as I just typed into chat, I apologize for missing all of the Twitch messages. I am so sorry about that. I seem to be seeing them now, so if you would like to re-ask them, I don't think I have any way of going back and seeing old questions that I missed earlier, but yeah, they definitely were not coming through. I was not seeing them at all. So thank you to you know who you are for sending me that email and letting me know. So I am now a little bit concerned about why that happened. That never happened during the 470 streams. also just noticed that it had turned on the stream, and I probably started dropping frames at that point. I'm also curious if the quality was, so obviously it just took a turn for the worse because I had the stream open inadvertently, but I'm curious as to whether the bit rate before that was a little bit better than yesterday. For those of you who were there yesterday, because I'm now broadcasting over an Ethernet connection instead of a Wi-Fi connection, although I also have Zoom open today, so I would expect it to be a little less performant for that reason. Okay, anyway, I seem to be getting messages from both places now. So, okay, so let's talk about the project. And if questions come up, I will backtrack if I need to. Okay, so yeah, so let's talk about how you would test these. But first, actually, let's just go ahead and do that. So if we want to test these interactively, then the way to go about doing this is to just run SWI prolog. We want to go ahead and read in all of our facts, and then we want to read in our solution P5. And so as we work on our solution file P5.pl, then we'll only have to reload that file basically because we're not changing the facts file. So so let's check and see. So let's test parent. So if we look at the documentation for parent, so the way we should read this is X has parent Y. So that is the way that we read this predicate. All right, so X has parent Y if and only if, right? And so we'll need to put those conditions there. But first, let's verify that this is not working. So remember that before the definition looked like this, where basically we just said anybody is the parent of anybody else. And so this will work for, some pairs of things, right? So for instance, we know that Kelly has parent Bill. So this should be true, and it is currently true. But we could also say, does Kelly have parent Ethel? And that is definitely not true, but that is currently returning true. And that's just because with this definition of parent, basically anybody has, this is true for any pair of atoms. Okay, from the Twitch chat, which I can see now, I was just asking about the cut. Is that an exclamation point, and what exactly does it do? Yeah, so the exclamation point is the cut, and let's see here. Let me just suspend this and show you. So this was, so in the lab definition, we use the cut operator here to just say, as long as we can prove all these true in one way, we want to stop looking at that point. We don't need to prove this in multiple ways. So as long as we can prove that these tests are passing in at least one way, we don't have to keep looking. Because remember that some of these predicates are possibly true in multiple ways. So for instance, so what's a good example? So looking back at the diagram, so those of you who are on Twitch, let me show you here. So if you look back at the diagram, for instance, Simula or C++. So C++ has Ancestor algol, C++ through Smalltalk and Simula, but C++ also has Ancestor algol through C. So there are multiple ways of proving that C++ has Ancestor algol. And so the cut operator just says that we are going to stop after we find the first such way of proving things. Okay, so all right. So let's think through this first definition, and then I think that that's all I'm going to solve for you on stream. But I would, of course, be happy to take questions at that point, so maybe you can go ahead and start queuing up questions. But so this first one is X has parent Y. And so we need to think about how we can define this with what we have to work with, which is, so if we were to get both of these on the screen at the same time. So this is the relationship that we have to work with, right? X has parents Y and Z, right? So this is a three-way predicate. And so what we want to do is define this two-way predicate. And so this is basically just kind of a compressing of the information from the three-way predicate. So X has parent Y, and hopefully at this point you can sort of see how you would define this. Anybody in the Zoom want to suggest a solution here? Did I lose the folks in Zoom now? Oh, okay. Just thinking. And by the way, remember that the Zoom audio is not going to the broadcast, so you can feel free to chat without knowing that other people are listening to you. So the way to think about this, right, is that we want parent Kelly Bill to be true, right? Because we know that Kelly has parent Bill. We also know that Kelly has parent Mary, right? So we want both of these to be true. And the only fact that we have to work with is this one fact right here, which says that Kelly has parents, plural, Bill and Mary. So what that should suggest to us at this point is that we will need two cases for this predicate. So we will need to say, so abstracting this a little bit, so we want to be able to say, you know, Kelly, yeah, so we know this is true, right? Because we know parents, Kelly, Bill, and Mary, right? And we also know this is the case because parents, Kelly, Bill, Mary. So the difference here is where the piece that we need to prove this statement is residing. So here, this is the piece that we need in order to prove it. And down here, this is the piece that we need to prove it. So in some sense, we can think about this top one as not needing Mary, right? We can prove that Kelly has parent Bill, assuming that Kelly has parents, Bill and anyone else. Similarly, we can prove that Kelly has parent Mary if Kelly has parents anybody else and Mary, right? So hopefully this now should suggest how we get to the definition here, because now we just need to sort of replace these specifics with variables. So wherever we see Kelly here, we'll replace it with X. And then in this definition, this is going to be, Bill is going to be Y. And then in this other definition, Mary, we could make this a different variable, but we don't really need to. Oh, I forgot to replace this one. We don't really need to make this a different name because these are different definitions, right? So this is one definition of parent, and then this is another definition of parent. So these are independent in that sense. But this is one way, one valid way of defining this. So hopefully now, if we reload P5, and again, we don't need to reload the facts file, we are just reloading our solution. So now Kelly parent Bill should still be true, it is, and parent Kelly Ethel should be false. So now we have a definition for parent. And then I guess the last thing I would mention here is that we don't actually need to use Z here, right? We could have just used Y here because these are sort of independent definitions. So this will work just as well. And actually at this point we can verify, I think this is actually an acceptable definition of this whole thing. Yeah, so we are now passing the, so at least according to the tests that we provided for you in the distribution, this is passing all the tests for parent. And so then I guess just the last thing that I would say about this is that this is one way of writing this. Another way of writing this is to use the OR operator. So a semicolon reads as OR in Prolog. So we could put this all on one line by using that OR operator. So X has parent Y if the parents of X are Y and something else, or the parents of Y are something else and Y. So that's how you would read that. And if we rerun the test, we'll see that that is also still passing. Okay. Again, I think that that is all I'm going to work for you. But you should be able to step through and think about all the other solutions based on what we've done. If you have questions, now would be the time to ask them. And then as you work this, just also keep in mind that, so remember from the lab solution that there were a couple other tricks that we needed at various points. One trick is being able to say that two things are not the same thing, so two variables are not the same, so you can do that using the /= operator. So this is kind of like in most languages you would write not equals, right? So this is kind of like Prolog's way of saying not equals. And then the other thing is that we needed a way of saying, not of something else. So this is kind of Prolog's way, the /+ is kind of Prolog's way of saying not. Okay. That is basically all I was planning to show. So that is the complete lab solution, a discussion about the programming assignment and the solution to the first part of that, which I'll go ahead and bring back up in case folks are needing to look at it. So these two solutions, so this is one way of defining parent, and then here is another way of defining parent. And those two are essentially equivalent from Prolog's point of view. Okay, well, that was a lot of me talking. Any questions?